Assalamualaikum. So for now we will be presenting our project assignment which is on microwave passive filter using insertion loss method, and this was presented by Muhammad Hazid bin Zamri and myself Intan Nashaira binti Masahi.
Okay, so this is the introduction. First one, a filter is a two-port network that controls the frequency response at a specific point in an RF and microwave system. The insertion loss method uses network synthesis technique to design filters with a completely specified frequency response. The method is often used to design high-performance filters when the desired frequency response is known. Richards transformations can be used to convert the lump elements to transmission line sections. Kuroda's identities can be used to physically separate filter elements by using transmission line sections.
Okay, next I will continue for the theory part. In insertion loss method, the relative power loss due to the lossless filter with reflection coefficient is specified in the power loss ratio. So basically there are four types of low pass filter, includes maximally flat, equiripple or Chebyshev filter, elliptic filter, and linear phase filter. So maximally flat, also known as butterworth response or binomial, provides the flattest passband response for the filter order like shown in the figure, and in equiripple the passband response will have a ripple of amplitude, which is we can see in this figure. For Richard transformation is used to create an LC network using open and short circuit transmission line stubs, and then the Kurita identities are then used to construct a more practical microwave filter implementation by utilizing redundant transmission line section. So this is the Kurita identities that were implemented in this project assignment.
Okay, so this is the low pass filter part. The cutoff frequency that been given is 2.4 GHz. The insertion loss is 35 dB, which is at 3.4 GHz, and the ripple is equal to 0, which is it is maximally flat. So I use the formula omega equals to 2 pi f, and also omega c equals to 2 pi fc. Then we just insert the value of f, which is 3.4 GHz, and we get 21.4 GHz. For the omega c, we insert the value of cutoff frequency, and the value we get is 15.08 GHz. So then we use formula that modulus omega over omega c minus 1, and we get 0.42. So if you see at this graph, you can see at the 0.4 is here and the 35 dB is here. So our n is equals to 10. Then we follow the table, n equals to 10. Okay, so this is the low pass filter calculation. So we need to calculate 5 capacitance and 5 inductance because our n is equals to 10. Then for the capacitance, we have C1, C3, C5, C7, and also C9. The formula that we use is Rho times by G equals to omega C. So and we get the answer is 0.415 picofarad. Same as the other capacitance, we just use this Rho times G over omega C according to the G value on the table given. So for the inductance part, we use the G over Rho times by omega C. So we get the answer is 3.01 nanohenry. For the Rho, we assume as 50 ohm. So this is the circuit that have been designed according to the value of capacitance and inductance that have been calculated. Alright, so this is the Richards transformation. We have 6 parts, which is A, B, C, D, E, and also F. We find the value of Z1, Z2, and also n the power of 2. Okay, so this is according to the G value. Then we calculate Z1, Z2. After we get the value of z1 and z2, we calculate the n power of 2, and the formula is 1 plus z2 of divided by z1. Then we calculate the n power of 2 times by z1, and also n power of 2 times by z2. We implement this in 6 part, for in each part for A, B, C, and also A, B, C, D, E, and also F. Okay, so this is the transformation value that we calculate. We apply on this circuit. So this is the part which I talked about: A, B, C, D, E, and also F. Then for the normalized impedance, we just put the value that we get on the calculation, which is the Z1 and also Z2. So we put it here, the value. This is the normalized part, and for the denormalized, we need to multiply this value, all of this value, multiply by 50 ohm, and so this is the answer that we get after we multiply by 50 ohm. Okay, so this is the circuit after we do the Richards transformation. So we insert the value that we multiply by 50 ohm into this. We using the line calculation in ADS. Then we get the width and also the length for all of these uh, tools in this ADS. Then after we design this circuit, we need to do the layout, and this is the layout that I get for this low pass circuit. Okay, so this is the result or graph of 2 1 that I get from the circuit that I have designed before. So as we can see, on the left side is the before tuning graph or before tuning result, and we can see that the graph is wavy, and on the right side, the tuning graph, after I tuning the length of each M link, and I get this result as my graph after tuning.
For bandpass filter, since center frequency is given, which is 2.4 GHz, so we calculate the lower cut-off frequency, we get 2.27 GHz, and upper cut-off frequency we get 2.53 GHz. And then the number of order is given, which is 3. So we refer the element values for equiripple, and we take this G1, G2, and G3. From those values that we obtained earlier in the calculation, so we put in this formula, so we get the inductance value and also capacitance value, and then those value we put in the schematic circuit in which is we construct in ADS. So after construct and run the simulation in the circuit, so we get this graph which is shown a band pass filter. We can see that there are lower cut-off frequency, higher cut-off frequency, and also a center frequency which is 2.4 GHz, and it has met the requirement in the questions given.
Okay, this is the discussion, and this is for the low pass filter. So the design of a low pass filter requires two distinct approaches, which is a lumped approach and also a distributed one. So the insertion loss method is used to determine the lump design circuit. Since the filter is maximally flat, its order can be determined by referring to the maximum flat elements values table and the attenuation versus normalized frequency graph for maximally flat filter prototypes. So the last one, as we know, the insertion loss of the filter is 35 dB at 3.4 gigahertz, and also the cutoff frequency is 2.4 gigahertz.
As for band pass filter, we have designed the band pass filter in ADS with first element is shunt inductance and capacitance, then followed by the series element. And then the result shown the frequency and S21 of the filter were measured and the passband response was obtained. And the results show that the filter has a passband 0.5 dB ripple and a center frequency of 2.4 GHz. And the filter was designed to be environmentally friendly and sustainable for the passband response. As for conclusion, the layout of lung low-pass filter is designed to reduce noise and interference from high-frequency signals, and the filter is designed to provide a smooth transition between the passband and also a stop band. As for bandpass filter, it has two cutoff frequency and a center frequency that allows signal within that band to pass through. And the passband filter are used in applications such as radio receivers and oscillators, where they are used to select signals at a particular frequency from a noisy environment. And then the incision loss method is advantageous over the filter design technique since it provides a higher degree of accuracy. So that's all from us. Thank you.